Let's now look at our final set of functions, which are hyperbolic functions. These are just defined through the exponential function. Let's have a look. We first start by forming the function from e to the x and combine it with e to the minus x, and basically define this as something called hyperbolic cosine of x, or cosh for short. And similarly, we take e to the x and minus e to the minus x and form the function sinh x. Some people call it shine x. These are defined for all x in R, simply because the exponential is also defined for all x in R. We can also define hyperbolic tangent, or tanh x, as sinh over cosh. Cosec and sec also have similar definitions to trig. Now, what is the reason for defining these? Well, it turns out they behave a little bit like trigonometric functions. Let's have a look at the combination cosh squared minus sinh squared x. So all I've done there is insert the definitions and square them. And what we can see is that the exponentials in these two things cancel out. And what we're left with is just 1. This is very similar to the trig identity cos squared plus sine squared equals 1. It turns out every single trig identity has an analogous one for the hyperbolic functions. So for example, if I consider sinh x cosh y plus cosh x sinh y, what does this become? Well, let's just work it all out. So all I've done there is insert the definitions into this. And if I expand all this out, what I find is that this is equal to 1 over 2, which is just equal to sinh x plus y. And in fact, each trig identity has an analogous one for hyperbolic functions, just with the rule that products of sinh get a -1 factor. Let's now have a look at what these functions look like. So on this plot, what we've got is hyperbolic functions cosh, sinh, and tanh. And for reference, we've got the exponential functions which make them up. E to the x and e to the minus x. So let's look at those first. E to the x is this thin blue line here, and e to the minus x is this thin blue line here. Cosh is just the sum of those two things, which produces this thick blue curve. Note that it's an even function, so it has a reflection symmetry around x equals 0. Sinh is the difference between the two exponentials, and this produces this brown curve here. And it's an odd function. And tanh is the ratio of those two things. It goes through 0 at the origin and then hits off to 1 as we go to plus infinity. The inverse hyperbolic functions are relatively easy to define, except for cosh, which doesn't pass a horizontal line test, so it only has an inverse function for positive x. So we define them in the usual way. Now, in fact, these can be related to the log function. These seem a little bit strange at first sight, but they're quite easy to work out. Let's have a quick go at one. If y is the inverse sinh of x, then sinh y is equal to x. And from the definition, this is just a half e to the y minus e to the minus y. If I multiply through by e to the minus y, this implies, and in fact we can see this is just a quadratic in e to the y. If I write, and if I solve this, and of course we need this to be positive, so we therefore take the positive root. The logarithm of this, which equals the result stated earlier. So that's just a brief overview of hyperbolic functions. We'll see when we get to complex numbers that hyperbolic functions and trigonometric functions are actually intimately related.